1.
Welcome back to the second part of Chapter 8. This is going to be sections 6, 7, and 8. There's only 3 sections, and we're going to be looking at radical expressions and functions and things like that. We'll get into what these are in just a minute, but today we're going to be looking at radical expressions and rational exponents. So, if we wanted to look at our learning targets, the first one will use the entire title of the topic. I can rewrite radical expressions using rational exponents. Not to be outdone, the second one will also use the entire title. I can simplify and evaluate radical expressions and expressions involving rational exponents. Hey, you're probably thinking, what are these radical expressions and what are these rational exponents? Well, we'll talk about radical expressions first. So, what radical expressions are not? We hear the term radical all the time in the news, everywhere. And it's a whole bunch of people being wrong is pretty much it. So, a quick Google search shows definition for radical. A bunch of definitions. I'm actually I kind of like there's a chemistry definition down there. That's kind of fun. But still, not what we're doing. This is not radical expressions. We hear about the radical expressions and radical agendas from the left and the right and everywhere in between. Nope, also not what we're talking about. And then we also get the word radical as in radical, like something the Teenage Mutant Ninja Turtles would say. And while, yes, I did watch a couple of these movies in preparation for this, that's not what we're actually talking about. So, what are radical expressions? Radical expressions are just a fancy word for roots. Square roots are radicals. But radical is the more generic term, because a square root has specifically, this is a 2. We don't write a 2 there, but it would be a 2. Well, radicals also include things like cube roots, 4th roots, 5th roots, 17th roots. We won't be working with those so much. But it's just roots of various degree. And so a little bit of vocab. This number that goes right here where it says radical is called the index. And the one over here underneath is called the radicand. That doesn't mean there's something called a radicant. It's not a radican, it's a radicand. And so it involves roots. An interesting topic, the square root of the answer company they started out making shoes. What kind of shoes did they make? They made shoes that skateboarders who would say radical would wear. And so this is a radical company. I'm sure that they didn't think about that at the time, but they were very, very math aware, even though they were completely unaware. And so we have these radicals. The first thing we're going to do is we're going to be simplifying these radical expressions. We already know how to do this. We did this back in chapter 1 with square roots. It's the same process with a very slight modification. So if we look at a square root, I chose a big one. We're going the square root of 200 times x to the 5th. How would we simplify this? We're going to first look at the 200, and we're going to factor it. Because remember, the square root is like a prison. It's going to take 2 people, 2 numbers to make a break for it. One will make it to the outside, the other will get shot and die. So, we're going to factor this 200. And there's a bunch of ways to factor it. I'm just going to do the way that I already have up here. It's hard to get question answer at this point. So 200 is 20 times 10. 20 is 2 times 10. 10 is 2 times 5. This 10 is also 2 times 5. So if you wanted to factor it a different way, 200 is 2 times 100. 100 is 10 times 10. You're going to get this. It's the prime factorization is unique, and so no matter how you factor it, you'll always get those. All right, so back to our square root. It takes 2 to break out. Well, we have a pair of 5s here. They can make a break for it. One will make it to the outside. The other will get shot and die. We have a pair of 2s. They can make a break for it. One will make it to the outside. So we're going to have a 2 and a 5 on the outside. They're going to multiply, and so we'll end up with 2 times 5 is 10. And on the inside, we have this one lonely 2 here. Notice we're not looking at the 10s or the 20. It's only the stuff at the bottom of the factor tree. So we have a 10 on the outside and a 2 on the inside. And then we can look at our variables. We don't really need a factor tree for the variables. X to the 5th is x times x times x times x times x. There's 5 x's there. How many pairs do we have? 2, with 1 left over. And so we get the 10, 2 times 5, x squared, because we had the 2 x's. And then left over, there is a 2, and that other x left on the inside. And so that was a harder question than we generally deal with, but it's still the same exact process. And this is the same process that we'll use for any other radical expression. The difference is that they might be higher security prisons. The square root is a low security. It only takes 2 of them to make a break for it. A cubed root is a higher security. It'll take 3 to make a break for it. A 4th root, it would take 4 to make a break for it. A 17th root is like super jail. It would take 17 to make a break for it. And no matter how many make a break for it, always 1 will make it to the outside. The rest get shot and die. So let's take a look at some. We have a cubed root here. So we can factor 8 is 2 times 4. 4 is 2 times 2. Hey, look, we have 3 2s. Takes 3 of them to make a break for it. So these 3 2s make a break. 1 makes it to the outside. And then the x's, hey, we have 3 x's. They make a break for it. 1 makes it to the outside. What's left inside? Nothing. That's okay. We just end up with 2x. A bit harder one. Here we have the cube root. Now we can split this up to be the cube root of the top and the cube root of the bottom, which should go right here. Anyway, that'll show up here in a minute. But we can do the cube root of the top and the bottom separately. The top, 125, we could do a factor tree, or we can think, well, that's 25 times 5, and 25 is 125 is 5 times 5 times 5. A lot of these you're going to be seeing over and over and over again, and you're going to figure it out. You're not going to have to factor tree it. Like 8 is 2 cubed. 16 is 2 to the 4th. 32 is 2 to the 5th. 64 is 2 to the 6th. 3 squared is 9. Cubed is 27. To the 4th is 81. 4 squared is 16. Cubed is 64. To the 4th is 256. You're going to see those over and over, and they're just going to start getting natural. We don't do too many that are really big because that just gets tedious. Anyway, 125 is 5 times 5 times 5. So that's 3 of them. The 5 makes it to the outside. X to the 6. How many groups of 3 do we have there? It's 2 with none left over. So it'll be 5x squared. Oh, there's that piece. Hey, we split it half and half. Or we split it top and bottom. We can do cube root of both. Anyway, we can simplify the top. 5, 5, and 5. Then x squared. And the cube root of 6 we can't do anything with. Well, we don't like having roots in the denominator. We do the rationalize the denominator thing. If this was a square root, we'd multiply the top and the bottom by the square root of 6. Because the square root of 6 times the square root of 6 equals 6. That's because that would make 2. Here we only have 1 6 here. So how many more 6's do we need to get it out of this cubed root? That's right, we need 2 more because we need 3 of them. So instead of multiplying just by cube root of 6, we need to multiply by the cube root of 6 times 6 to both the top and the bottom. So that's the cube root of 36, and the denominator is just going to be 6. So it ends up looking like that, 5x squared times the cube root of 36 over 6. Again, this is a bit bigger of one than we would typically be doing, but we can see that we can do it. And this includes rationalizing the denominator as well. I know a lot of people look at that and see, well, the cube root of 36, you you can simplify root 36. You can simplify the square root of 36, not the cube root, because 36 is 6 times 6. Each of the 6's is a 2 times 3, so you've got 2 2's, 2 3's, and no 3 of a kinds. So this is as simplified as this one gets. I know it doesn't look very simplified. Just going to have to deal with that. Let's do one more. The fourth root of 32 over x to the fourth. So again, we can split it up, just like we did this one, to the fourth root of 32 over the fourth root of x to the fourth. We can factor 32. 32 is 8 times 4, 16 times 2. It could be a lot of things. Then 8 is 2 times 4. The 4 is 2 times 2. This 4 is 2 times 2. And so look, 32 is 2 to the 1, 2, 3, 4, 5. It's 2 to the 5th. Well, we have 4 2's here that can make a break for it. So one of them can get to the outside, and there's one left on the inside. And in the denominator, we have 4 x's. They make a break for it. One makes it to the outside, and there's nothing left in the denominator. And notice that this 4 here, the index, does not change. So we have 2 to the fourth root of 2 over x. These look confusing. A little bit of practice helps with these, because it is exactly the same stuff as we were doing in chapter 1 with square roots, but it does take a little bit of practice. So let's move on to the radical form and rational exponents. What are we going to do with these, and what are rational exponents? Well, rational exponents, we can break up the word. We have exponents, we know what those are, and we have rational. What does rational mean? Well, the whole first half of the chapter we're dealing with rational expressions. That would be fractions. These are going to be fractions in exponents. It's like two great things combined to be one. It's fantastic. So we'll get things that look like x to the a over b, where a over b is the exponent here. I know sometimes the font, it just makes it a little bit too big, so it looks like x and a over b. This is x to the a over b. Well, what does this mean? We can rewrite this as a radical, as a root, and we can go back and forth with that. So when we do this, the a is the exponent, and the b is the index on the root. These two things mean the same thing, x to the a and the bth root of that. So the b just becomes that. We could also write it. It doesn't matter if we do the exponent first and then the root, or the root and then the exponent. So we could rewrite this as the bth root of x, then to the 8th power. Sometimes, especially if we're simplifying, this is going to be a lot easier, and we'll see that in just a minute. And so with these, sometimes we're going to be taking it from a rational exponent and making it a root. Sometimes we're going to be taking it as a root and making it a rational exponent. This is kind of like when we first learned about logs. We were going between exponential functions and logs, and then logs and exponential functions, where we were just rewriting them. But we'll probably be simplifying a little bit too. So, see here, write in radical form and simplify. So now, when you get directions like this, there are 2 steps to this. Write in radical form and simplify. It's like part A, part B. If you just give me a number for an answer, hey, you may have simplified. That's not answering the full question. Make sure you answer both pieces. So something like 36 to the 3/2. We can rewrite this. This will be, so we have 36 to the 3/2. That'll be 36 cubed. And then the 2th root, that would be the square root of that. A lot of times we don't typically put the 2 there for the index when there's not, it just means 2, like the square root you've been using for years. I put it here just for the example purpose. So we have 36 cubed in the square root. And so here, well, 36 cubed, it's going to be a pretty big number. So instead of writing it like this, might it be easier to write it like this? Can we do the square root of 36 and then cube that? So instead of making the number really big, we can make the number smaller first. It's a lot easier that way. So I'd write it like this. The square root of 36 is just 6, so we have 6 cubed, and 6 cubed is 216. There we go. We wrote it in radical form, either one of these, and then we simplified. Fun story, if you put 36 to the 3 halves in your calculator, it will give you 216. Your calculator will do these, but it doesn't put it in radical form for you. So yes, you still do need to show it, but you can check your answer pretty easily. Let's look at another one. 32 to the 3/5. Same idea. Let's just skip straight to this one, though. We're going to have 3 as the exponent, but now our index is going to be 5. So we have the 5th root of 32 cubed. Well, what to the 5th power equals 32? If you had to take a guess, no, it's not going to be 1. 1 to the 5th is still 1. It might be 2. 2 to the 5th is 32. 3 to the 5th is 243. They get big very, very quickly. So 32, yeah, if you had to take a guess, hey, how about 2? Let's see, 2 times 2 times 2 times 2 times 2. Hey, that's 32. Look at that. So we get 2 cubed, which is 8. 2 times 2 times 2. Again, the powers of 2, you're going to get pretty familiar with. This one won't be too hard just to look at and be like, oh yeah, that's going to be 2 pretty quick. But there we get 2 cubed. 2 times 2 times 2 is 8. It is not 6. People are like, so 2 times 2 is 4 times 2 is 6. No, 4 times 2 is 8. And how about negative 27 to the 1/3? So in radical form, that'll be the cube root into the first power. So we have the cube root of negative 27. You're probably thinking, wait a second, we can't have a negative under a square root. True. You cannot have a negative under a square root. Under a cube root, however, it's fine. The problem with a square root is what times itself gives you a negative. We have a positive times a positive is a positive. A negative times a negative is a negative. But with a cube root, a negative times a negative times a negative is a negative. I think a second ago I said a negative times a negative is a negative. That would be a negative times a negative is a positive. That's why a negative can't be underneath a square root. But a cube root, negative times negative is still a negative. So we could actually take this negative out of a cube root and put it out in front. Then cube root of 27, what times itself 3 times is 27? Well, 2 is just going to be 8. How about 3? 3 times 3 is 9, times 3 is 27. So it's just the negative 3. So with the negatives, under odd roots, if it's an odd index, the negative is fine. If it's an even index, that's a problem. That's where we start getting into imaginary numbers. But you shouldn't have to worry about that so much here. If you get a negative, it should be an odd root. So this is one thing we could do. We can write in radical form and simplify. So we go from the rational exponent to the root, and then simplifying down to a number. The other thing is we could go the other way. We go from a root to a rational exponent. This one doesn't say simplify. We're going to, just because I think it's kind of fun. We can see how some of the exponent properties work, but I'll show you where you can actually stop based on the instructions. So we have the 5th root of 9 to the 10th. Looks like this. So that's 9 to the 10 over the index, 9 to the 10 over 5. Technically, this answers the question, right, using rational exponents. But we could simplify this. 10 over 5, isn't that just 9 squared? 9 squared is 81. See, all the fraction rules still apply. All the exponent rules still apply. It's like, I don't know, it's so... almost magic that these things come together and all the rules that we've known for both things still work and it holds mathematically, and it's just awesome. So anyway, this one's 81. Let's look at another one. The 6th root of 5 cubed. Well, the 6th root of 5, let's see, that looks kind of like this one. So b is the denominator, a is the numerator, so that'd be 5 to the 3/6. This is written using rational exponents. But 3/6 is just 1/2. That's 5 to the 1/2. And 5 to the 1/2, is that 5 to the 1, but the square root? It's the square root of 5. So the 6th root of 5 cubed is the square root of 5. It's craziness. Another one, square root of 8 cubed. So it's like this. So the a is 3, but there's no b. What number would go there if there's no number there? No, it's not 1. No, it's not 0. Remember, this is a square root. That's always been a 2. It's just, we don't put it there. So this would be 8 to the 3/2. Simplifying this one's a little bit rougher because you have to go 8 cubed and then the square root of that because it doesn't square root well. Really, 8 is 2 times 2 times 2, so there's 3 2's. Cubed is going to be 9 2's. Divide, and then square root of that. That makes 4 groups of 2, so it's 4 root 2. Anyway, I wouldn't go past that one there since we don't have to. So one of the things, you're just writing them back and forth, and then practice simplifying roots. And here, a lot of times, if you're going to simplify, you'd simplify with roots anyway. But we're going to do some simplifying as well. And I mentioned that all of the exponent properties hold, all the fraction properties hold. This is where this comes in handy. So things like 13 to the 1/2 times 13 to the 3/2. Or multiplying two things with the same base, which means, what can we do with our exponents? We can add our exponents. 1/2 plus 3/2, we have 13 to the 4/2. Well, 4/2 is just 2, so it's 13 squared. And 13 squared is 169. Simplified. It's way easier than doing the square root of 13 times 13, the square root of 13 cubed. Yeah, nope. Simplify, combine. We can simplify our exponent, and then 13 squared is 169. How about something like 64 to the 1/2 to the 1/3? Well, we have a power of a power. When you have a power of a power, you multiply the two powers. And so 1/2 times 1/3 is 1/6. 64 to the 1/6. That'll be the 6th root of 64. What times itself 6 times equals 64? Based on our numbers, probably 2. And look, 2, 5 times equals 32. Well, 32 times 2 is 64. 64 is 2 to the 6th. And so that's just 2. Another way you could have done this is 64 to the 1/2. That's the square root of 64. That's 8. And the cube root of 8 is 2. So you could have simplified that either way, and it actually would have worked out pretty easily. Division. So we have the same base. When we multiply with the same base, we add the exponents. When we divide with the same base, we subtract the exponents. So we have 9 to the 4/3 and 9 to the 2/3. 4/3 minus 2/3 is just 2/3. And now we can square this and cube root it. And I would recommend doing it in that order because the cube root of 9 isn't going to be pleasant. So we'll square it and cube root it. 9 squared is 81. We can factor 81. Well, it's 9 times 9. And each of the 9s is 3 times 3. 81 is 3 to the 4th. So that'll be 3 times 3 times 3 times 3. we're looking for 3 of them to make a break for it. So we get 3 that make a break for it, 1 makes it out, and there's 1 left on the inside. So we have 3 cube root 3. 8 over 27 to the 1/3. Well, just like on the other page when we were simplifying roots, we can do the top and the bottom completely separately. So we can go 8 to the 1/3 over 27 to the 1/3. That's going to be the cube root of 8 over the cube root of 27. What times itself 3 times equals 8? Oh, 2 cubed equals 8. And what times itself 3 times equals 27? Oh, the cube root of 27 is 3. See how these same numbers keep popping up over and over and over again? Anyway, this one is 2 over 3. Now one more, just for good measure. 7 to the 1/4 times 7 to the negative 3/4. Right? Just like over here, we're multiplying. So we add the exponents. 1/4 plus negative 3/4 is negative 2/4. So we have 7 to the negative 2/4, which is 7 to the negative 1/2, which the negative means it's going to be 1 over 7 to the 1/2. The 1/2 is a square root. This we could rewrite as 1 over the square root of 7. Well, we don't want to have a square root in the denominator, so we can multiply by the root 7 over root 7. When we do that, 1 times root 7 is root 7, and root 7 times root 7 is just 7. It doesn't go away. We end up with root 7 over 7. And that would be as simplified as this one gets. This one's fun because in addition to all the other properties, we have negative exponents in here. Even negative exponents hold true with the fractions. It's phenomenal. I love it. Anyway, this is the kind of thing that you're doing. Be ready for some problems to work in class. They probably won't be quite to this level, but be ready for some problems in class. And don't forget to post a comment. And I will see you later.